Well, hello again, advanced geometry students. How you doing? This is Mr. Sunderland. Thanks for checking out this week's lesson. And this week's lesson will be on what is called the law of sines. I'll show you in a minute where we use the law of sines, but our objectives this week are to figure out how to use the law of sines to solve for missing sides, and how to use the law of sine, specifically inverse sine, to solve for missing angles. And as you'll see later, all of these occur when we do not have a right triangle, but we can still use the law of sines to solve for missing parts. We will also do a little bit of review starting right now. So I've got 3 problems here for you. Whenever you feel ready, go ahead and pause and see if you can solve for all missing sides and all missing angles using sine, cosine, and tangent, and inverse sine, inverse cosine, and inverse tangent where appropriate. Go ahead and hit pause and solve for all of those, and I will reveal the answers momentarily. So in this first triangle on the far left, if you're using it the way it is written now, and I use 43 degrees, 12 would be my adjacent side, this would be my opposite side, so we can use tangent. You would have ultimately done 12 tan 43 to get something slightly less than 12. Because I know this is a right triangle and one angle is 43, then my last angle is the complement of 43, which would be 47 degrees. Now that you've got 2 out of 3 sides in a right triangle, remember you can always use the Pythagorean theorem, or you could still use cosine or sine if you wanted to solve for that last side, but you would get 16.41. Okay, in my middle example here, if I use 35 as theta and 7 as my opposite side, then you could go ahead and use either tangent to get my adjacent side or sine to get my hypotenuse. If we were getting the hypotenuse, it would be 7 over sine 35. We get 12.2. When I get my other leg, we could use Pythagorean theorem or tangent like I said before. And then my last angle is just the complement of 35 degrees, which would be 55 degrees. Now in this last example here, it's nice. We do see we have a 5, 12, 13, so using a Pythagorean triple, maybe you get 5 right away. You could also solve for that using Pythagorean theorem, or we could do inverse trig and then use trig later. But once you know 2 of the 3 sides, Pythagorean theorem is always a nice trick to get that third side. And then if I was to solve for this angle, I could use inverse sine of 12 over 13. I could use inverse tangent of 12 over 5. I could use inverse cosine of 5 over 13. Any of those ways would get me an angle of 67.38 degrees, and then 22.62 degrees for my other angle here. Hopefully that review is going well and you feel pretty good about sine, cosine, and tangent and their inverses in order to solve for sides. What happens if we get to something like this? You might be thinking, well, sine, cosine, and tangent don't really help me too much here. Now you could pencil in the height here and kind of break the triangle down, and that would be a great approach. But a shorter approach to doing that would be what we have coming up. Now as you see here, it's not a right triangle, so that's why it's nice to have what is called the law of sines. Okay? And just a reminder, anytime you're going through these videos, or these of the lessons, pause whenever you need to. Write down these notes and put them in your notes. You should be writing stuff and adding them to your notes all the time. Don't just not write anything down because it's on a video. Okay? It's good to have these notes handy for when you are doing the homework, and you can just bring up your notes rather than having to go back and check out the video. I think you'll also end up retaining a lot more if you're taking notes of the lesson as you're going. But these are the exact same rules here. One is just the reciprocal of the other, but not a ton of teachers do this, but I like to have let me back up for a second. A way we typically refer to triangles, and I think this may have already come up in the class, I'm not quite sure. I don't even know what day it is anymore, you know? But in this triangle, you'll see that I have capital letters for all the vertices, for all the angles, and then lowercase letters across from those capital letters to represent that side. For example, here's my capital letter A, across from A is lowercase a, the side across from angle A. Angle B, side B, angle C, and side C. Okay? So when we're using the law of sines, I like to have the sides on the top when I'm solving for a side, and I like to have sine of the angle on the top when I'm solving for an angle. And I'll show you when we're putting this into practice why that's a little bit more useful. It just kind of gives you one step to get whatever it is you're solving for by itself. Okay? A quick derivation of the law of sines, and this isn't something you'd be asked to show on a test. However, some of you might be the kind of people that like to know, well, why? Why does the law of sines work? Where does it come from? If that's you, that's awesome. You should always be asking, where does this rule come from? Because if you can actually derive these things on your own, you have a much deeper understanding of how to use them. But the way we can show it is if I pencil in my height here into the triangle. Let's go ahead and solve for x using angle A. I could say that sine of A equals x over B. Similarly, if I use angle B, I could say that the sine of B equals x over side A. Remember, sine is opposite over hypotenuse. So if you're at B, x is the opposite and A is the hypotenuse. If I'm at angle A, and I'm using just this right triangle on the right, x is the opposite and B is the hypotenuse. Well, what do both of these equations have in common? They both have an x. So if I solve for x and set those equal to each other, we end up getting something like this. B sine A equals A sine B, which would allow us to show very easily just dividing both sides by A, dividing both sides by B, we have the law of sines. And you can use a very similar argument to extend that to be sine of C over C. Again, being able to derive these things is not necessary, but I would not be doing my due diligence if I didn't at least show you where it came from. Anyways, let's put it into practice though. Here is that first example we had, where I've got 40 degrees, 35 degrees. My third angle would be 105 degrees, so I know it's not a right triangle. There is no 90-degree angle in those three vertices. But let's go ahead and write in my vertices anyways. I've got angle A, angle B, and angle C. Okay? And we're going to, because I'm going to solve for x, which is an unknown side, we're going to use the version of the law of sines that involves sides. Now, we never typically use two sets of equal signs when we're solving this. The double equal signs, this extended proportion, just shows you how all the sides and angles relate to each other. But we don't use that in a problem-solving situation. What we use is just one of those, right? So I'm going to use side A, which is across from angle A, over sine of A, equals B, the side across from angle B, over the sine of B. And again, like everything else, guys, if you're getting a little bit intimidated by this right now, take a deep breath. It turns out to not be as hard as you think. Always does, okay? So let's plug in what we know. Side A across from angle A is x. Angle A is 40 degrees. Side B I know is 12. And the sine of angle B, 35 degrees. So when I plug in everything that I know, I have this proportion. Now I say proportion, and kids always want to cross multiply, but x just has one thing happening to it. What's happening to x? X is being divided by sine of 40. How do you undo division? Multiplication. So in getting x by itself, I just have 12 sine 40 over sine of 35. That's one move on your calculator. Check it out. You can just type this exact thing into your calculator, and boom, there's x. It's a little crazy looking. It's got two signs in it, but it's just one step on your calculator. And the more we practice this, the easier that really becomes. Okay? So going back, well, we use just our simple proportion here, plug in what we know, get x by itself by multiplying both sides by sine of 40, and we got 13.45. And again, here's how you can do that in one move on the calculator. Let's do another one here, okay? So I've got everything, enough information for you to be able to use the law of sines. Go ahead and hit pause and see if you can work the solution yourself. And we'll go over it momentarily. All right, so in solving for angle x there, I see it is across from angle C. I've got a side B and angle B. Okay, so in a way, what we're going to be using is this part of the law of sines. But as you're hopefully realizing here, it's really any triangle where I know 2 out of the 3 angles and 1 of the sides. Okay, that's when we can apply the law of sines. Plug in what we know. We're solving for x, so that's going to be on the top of our proportion. The angle across from x, sine of 63. The other side we know is 10, and sine of the angle across from that, so sine 41. To get x by itself, multiply both sides by sine 63, and there is everything we need to type into the calculator in order to solve for x. I type that in, I get 13.58. Here's what you can type into the calculator, 10 sine 63 over sine of 41, 13.58, boom. We'll do one more where you're solving this one again. Now, one thing you may be thinking, oh shoot, I don't know the angle across from R. But anytime we have a triangle, we know 2 out of the 3 angles. Add those up, subtract that from 180, and that's how we can get our third angle there. So I know my third angle is 35 degrees. If you're still struggling with what to do here, pause the video at any time, write this down, and see if you can solve on your own for side R. This is the initial thing we get when we use the law of sines. Now you may be saying, well, where did sine of A over B and C, where did all that go? We tend to not use that. Like I said before, if you know 2 of the 3 angles and 1 of the sides in any triangle, that's when you can use the law of sines. I'm solving for side R, so R over sine of the angle across from R equals another known side over sine of the angle across from that known side. Okay? So once I've got this proportion set up, hopefully you're thinking, okay, well, I know what to do from here. R is being divided by sine of 35, so you just have to multiply both sides by sine of 35. And there's our equation. That'll get us R. Here's what it looks like on the calculator. So there's our answer for R. Always be thinking if the question has units in it, then make sure to put units in your answer. Keep those units consistent and keep them in your answer. All right. Now, like I mentioned at the beginning of this, we can use the law of sines to solve for angles. Okay, here I've got a situation where I know one of the angles in my triangle and I know two of the sides, including a side across from that angle. There is another situation in math where if I didn't know the angle across from 103, but I knew the one next to it, that's when we'd use something called the law of cosines. And I'm not sure that remote learning is going to allow us to delve into the law of cosines. We'll see next week, but not quite sure. As for now, this is a situation because I know the length of the side across from 103, and I know the side next to 103, we can use the law of sines, okay? So we're solving for an angle, so I don't need this whole extended proportion. I'm only going to use part of it. And like I said, because we're solving for an angle, I'm going to put those angle expressions, or sine of the angle, on top of the proportion. So I didn't specify here, but let's say I'm trying to get angle A. Okay, and that's the only one I can solve for because I do know the side that is across from A. So just like the other ones, let's just plug in everything that we've got. I don't know the measure of angle A yet, but I know that the side across from angle A is 13. Sine of 103 over the side across from 103, 18. In one move, I can get sine of A by itself by multiplying both sides by 13. And like you learned with sine, cosine, and tangent, how do you go from sine of A to just A? Inverse sine, right? So you can do the inverse sine of that whole beast on the right there. So the inverse sine of 13 sine 103 over 18 sounds kind of crazy, but that's what these calculators are built to do. You can do that in one move on your calculator, like so. The inverse sine, 13 sine 103 over 18, close your parentheses, and we get that A is about 44.73 degrees. Now, just some things to think about. Because A is across from a side much less than 18, it's got to be an angle much less than 103. Hopefully you're also thinking, well, it can't be bigger than 103. You can't have two angles over 100 degrees, and that's a good point. But we look at our answer, it is much less than 103 degrees, so we should be pretty happy with our answer. Okay, so now you try. Let me just see what I've got here. Okay. We'll go through this one slowly. But if you want, go ahead and pause and see if you can look back at the work from the previous problem, set it up, and see if you can solve for angle C very similarly to how we did the last one. Set up your proportion, and then use inverse sine in the end. Go ahead and pause when you're ready and work the solution. Work the problem. Sorry, not work the solution. But let's go through it right now together. Because we're solving for an angle, I'm going to put sine of C over the length of C equals sine of B over the length of side B. And let's plug in what we know. I don't know angle C. I know that side C is 20. I know angle B, and I know the length of B. So plug in all that stuff. And we've got sine of C over 20 equals sine of 71 over 23. Just two simple moves. To get that sine of C by itself, multiply both sides by 20. And to go from sine of C to C, we don't use sine, we use the inverse sine. So we're just taking the whole inverse sine of that right side there. Okay? Inverse sine of 20 sine 71 over 23. And let's go back to the triangle first. We knew that B was 71 degrees, and it was across from a side length of 23 inches. Now angle C is across from a slightly smaller side. So I should expect and anticipate getting an angle smaller than 71 degrees. If I don't, then I made a mistake somewhere. So in continuing this problem, I got 55.3 degrees. Here's what that looks like on the calculator. Let me just scroll down here. Inverse sine of 20 sine 71 over 23 Type that into the calculator. Inverse sine of 20 sine 71 over 23. Close your parentheses. 55.3 degrees. Less than 71, which is what we were expecting and hoping for. Okay? Now I know that's a lot, but there'll be a homework on Pearson. I was having a little bit of issues just now getting into Pearson, so that should be ready for you by the time you watch this video. If it's not, shoot me an email. And we will have our Zoom session on Thursday to answer whatever questions you've got. Stay healthy, everybody, and let's hope that we get back to a normal world as soon as possible. Take care, SHS. Bye, guys.